So, we're going to talk about dot products and cross products. What are those? Well, you'll find out. So, if A and B are perpendicular vectors here, and vector BA is a vector between their terminal points, then this makes a right triangle, and the magnitudes of these vectors have to satisfy the Pythagorean theorem. Right, the magnitude of BA squared has to equal the magnitude of A squared plus the magnitude of B squared. Now, by definition, the magnitude of this vector is, again, using the Pythagorean theorem, right, the square root of the difference between the points in the x direction, right? So the ending x coordinate minus the beginning x coordinate, and the ending y coordinate minus the beginning y coordinate. So if we FOIL this out, right, so a1 minus b1 times a1 minus b1, if you FOIL this, you're going to get a1 squared minus a1 b1 minus a1 b1 plus b1 squared. So a1 squared will make this a minus 2a1 b1 plus b1 squared. And if you FOIL this one, you're going to get the exact same thing, except you change the 1's to 2's. So a2 squared minus 2a2b2 plus b2 squared. Now, just to make things a little bit easier, we're going to rearrange things. I'm not changing anything, I'm just rearranging. So I'm going to take my a1, I'm going to put my a's together. So I've got an a1 squared and an a2 squared. And I'm going to put my b's together. So I've got a b1 squared and a b2 squared. And then I've got this minus 2 a1 b1 and a minus 2 a2 b2. And then the length of this vector, right, again by Pythagorean theorem, and the definition of a vector, the length of vector A, magnitude of vector A, is going to be the square root of a1 squared plus a2 squared. Or, if we square both sides of that, the magnitude squared is equal to a1 squared plus a2 squared. So this a1 squared plus a2 squared we can replace with being the magnitude of A squared. And this b1 squared plus b2 squared we can replace with being the magnitude of B squared. And then we got this bit. I'm going to factor out a negative 2 here and make this a1 b1 plus a2 b2. So what we get here is that we get that, right, so what I should have done up here is squared this and get rid of the square root. So get rid of that square root there. And so what I get is that BA squared is equal to A squared plus B squared minus A1B1 minus 2A1B1 plus A2B2. But if I go back to the last page here, right, BA squared equals A squared plus B squared. So what do I do with all this extra junk? Well, it must mean that all this extra junk equals 0. And we can just get rid of that negative 2, right? It must mean that A1B1 plus A2B2 equals 0. So, we get that the Pythagorean theorem only works if and only if A1B1 plus A2B2 equals 0. This particular thing is frequently used in vectors. It's called the inner product or the dot product. When I learned it in school, we called it the dot product, which is probably what I'm going to call it most often, but your book calls it the inner product. It's the same thing. So, the inner product of vectors in a plane, all you do is you multiply the x coordinates together and you multiply the y coordinates together and then you add those. So your dot product is not a vector. Your dot product should be a real number, not a vector. So dot product of two vectors is not a vector, it's a number. So you would read this as a dot b. And so then you get this important rule, which we just proved. Two vectors are perpendicular if and only if their inner product is 0. So, to prove that two vectors are perpendicular, you find their dot product. If the dot product is 0, they're perpendicular. If the dot product is not 0, they are not perpendicular. Right? So, find each inner product. If vector p is 7, 14, q is 2, -1, and m is 3, 5. Are any pair of vectors perpendicular? So, p dot q, you multiply the x coordinates together, 7 times 2, and you multiply the y coordinates together, 14 times -1, and then you add them up. So that's 14 plus -14, which is 0. P and Q are perpendicular. Q dot M, you multiply the x coordinates, so 2 times 3, and you multiply the y coordinates, -1 times 5, and you add them up. 6 plus -5 equals 1. Not 0, not perpendicular. I can spell. QR. And then if we do P dot M, multiply 7 times 3, multiply 14 times 5, that's 21 plus 70 is 91, which is not 0, which means these are also not perpendicular. QR. Dot products are commutative, which means that you can do them in either order. So P dot Q is the same thing as Q dot P. Does not matter what order you do them in. Vectors in 3 dimensions, you can do the dot product as well. You multiply the x coordinates, you multiply the y coordinates, and you multiply the z coordinates, and you add them all up. It's exactly the same, except you have one little extra multiplication thing at the end that you add. It works exactly the same. And again, two vectors in space, in 3-dimensional space, are perpendicular if and only if their dot product is 0. Nothing different here, except for having the z's. Right? So, dot product for A and B, if A is -3, 1, 1, and B is 2, 8, -2, then A dot B, you're going to multiply the x's, so -3 times 2, you're going to multiply the y's, 1 times 8, and you're going to multiply the z's, 1 times -2, and you add them all up. So -6 plus 8 minus 2 does in fact equal 0, which means that these two vectors are perpendicular. Ta-da! Another important product involving vectors is the cross product. The cross product only works for three-dimensional vectors. No, that's, yes. So the cross product of two vectors is a vector. This vector is not in the same plane as the vectors. It's perpendicular to the plane containing the two vectors. So if I have a vector like this and a vector like this, my cross product is going to be perpendicular to these two vectors, which would mean that it's coming out of the screen, right? Perpendicular to the flat surface of the plane. So the cross product of two vectors is perpendicular to both vectors. And we write this as A cross B. So in order to do the cross product, you need to know a little bit about determinants. Little bit. We haven't gotten to matrices because we skipped chapter 2. We'll do matrices later this semester. So this definition doesn't make much sense. You can write it down if you want to, but here's how you do determinants. So the determinant of a 2 by 2 matrix, this is a 2 by 2 matrix. The determinant of the 2 by 2 matrix, you multiply the diagonals and you subtract them. So this would be 3 times 2 minus 1 times 1. And that is 6 minus 1. The determinant of this 2 by 2 matrix would be 5. Multiply the diagonals, and then you do this diagonal minus this diagonal. For a 3 by 3 matrix, you're going to do the same thing, except you're going to do it 3 times. So in order to do the cross product, we need to write all of our vectors as sums of the unit vectors I, j, and k. What we do is we start with I. So we're going to start with I, and you cross out that row, or column. We're going to ignore the I column. Now, find the determinant of what's left over. You can also think about it as crossing out this row. So, find the determinant of what's left over. So that would be A2, B3, minus A3, B2. Then we're going to do the J's. So you take J, and you cross out the top row, and you cross out the middle column, and you do the determinant of what's left. So A1, B3, minus A3, B1. And then you take K, and you cross out the top row, and you cross out this column, and you do the determinant of what's left. A1, B2, minus A2, B1. And then you subtract these and add that one. It's always a subtraction and then an add. Don't ask me why. I don't know. Just is. Okay? So, the cross product of V and W. So we're going to write vector V is 0i plus 3j plus 1k. And vector W is 0i plus 1j plus 2k. So then to put these in a matrix, I'll put the matrix up here. To put these in a matrix, I, j, and k We have one that's 0, 3, 1, and one that's 0, 1, 2. And so to do the cross product, we're going to start with I. We're going to cancel out the I row, the letter row and the I column. And we're going to do the determinant of what's left. So that's going to be 3 times 2 minus 1 times 1, which is 6 minus 1, which is 5i. Then we're going to take j. All right, so the j, we get a minus j. I'm going to take j. We're going to cancel out the other letters. We're going to cancel out this row. And we're going to do the determinant of what's left, which is 0 times 2 minus 1 times 0, which is 0 minus 0, which is 0j. And then we're going to take k. This is plus k. We're going to cancel out the top row. We're going to cancel out this column. And we're going to do the determinant of what's left. And so that's going to be 0 times 1 minus 3 times 0, which is 0 minus 0 again, which is 0. Okay. So we get a vector that is 5, 0, 0 as our cross product. So V cross W is the vector 5, 0, 0. In order to verify that this is perpendicular to both V and W, we do the dot product. I'm going to call this vector, let's call this vector C for cross product, just to make my life a little bit easier. So if I do C dot V, right, C is 5, 0, 0, and V is 0, 3, 1. You multiply the x's together, 5 times 0. You multiply the y's together, 0 times 3. You multiply the z's together, 0 times 1. And that's not a vector anymore. You get 0 plus 0 plus 0 equals 0. If the dot product is 0, they are perpendicular. And then we want to do C dot W. C was 5, 0, 0, and W was 0, 1, 2. And so we do 5 times 0 plus 0 times 1 plus 0 times 2, which is 0 plus 0 plus 0 again, which is also 0, which means that this is also perpendicular. Perpendicular. If I could spell, I'd be an English teacher. So, we found a vector that is perpendicular to V and W, and we proved that it's perpendicular by finding the dot product. In addition to being an actor, Emilio Estevez is an avid stock car driver. Drivers in stock car races must constantly shift gears to maneuver their cars into competitive positions. A gear shift rotates about the connection to the transmission. The rate of change of the rotation of the gear shift depends on the magnitude of the force exerted by the driver and on the perpendicular distance of its line of action from the center of rotation. Suppose Emilio Estevez is applying a force of 25 pounds along the positive z-axis to the gear shift of his car. If the center of the connection of the gear shift is at the origin, the force is applied at the point 0.750, 0.27. Find the torque. So the torque in this case is going to be the cross product of these two vectors. So, or the magnitude of the cross product of these two vectors, let's say. So we've got a vector here that is 0.75, 0.27, right? If we draw a vector from the origin to this point, and then he's applying a force of 25 pounds along the positive z-axis. So the x and the y-axes are 0 and 25 along the z-axis. And so we want to find the cross product of these. I suppose I could write this like this and save myself a little bit of work. All right, we want to find the cross product of these. Can't talk and write at the same time. We want to find the cross product of these two vectors. And that's going to give us the torque. So make our matrix I, J, K, 0.75, 0, 0.27, 0, 0, 25. So the cross product, start with the I, we cross out the column with the letters, or the row with the letters, and we cross out the I column, and we're going to find the determinant. And the determinant here is 0 times 25 minus 0 times 0.27, which is 0i. 0 minus 0 is 0. Maybe this helps if I put these in parentheses instead of using the dot, whatever. Then we're going to find j. Remember, we minus j. Cross out the row with the letters, cross out the j column. We do the determinant of what's left. So that's going to be 0.75 times 25 minus 0.27 times 0. And so that is 0.75 times 25 is 18.75 minus 0. And then we're going to do K. So cross out the row with the letters, cross out the K column, 0.75 times 0, and 0 times 0. And that's also 0. That's plus 0, K. So we get that the vector for the torque is 0, negative 18.75, 0. And torque should not be a vector. We actually want the magnitude of this vector. Right, the magnitude of this vector is going to be square root of 0 squared plus negative 18.75 squared plus 0 squared, which is the square root of negative 18.75 squared, which is 18.75. Yay, wasn't that fun?